1538 degrees centigrade. Now, I should tell you the story of an American scientist called Stephen A. Jones, who read these reports I just told you about, the preliminary findings in the dust. There was a woman called Janet McKinley who lived on the corner of Liberty Street and Cedar Street, here on this corner. She actually had a view of the plaza. And when the South Tower fell, because the tower which came down first, she took a wet towel, wrapped it around her face, and ran away. Very clever, because the dust is not very healthy to breathe. And she was allowed to come back to her apartment about a week later, and it looked like this. The windows were completely blown out. So she had quite a cleaning job to do. She had a spirit, I must say, I'm saying she had a spiritual mind because she passed away a few months ago from a brain tumor. But she had a very spiritual connection with this dust, and she understood the significance of the event. She saved some of the dust in a plastic bag, having the intention of making it into a piece of artwork later on. So accidentally, Stephen A. Jones, this American scientist from Brigham Young University in Utah, got a connection with Janet McKinley because he wanted to look into the dust. When you have an explosive event, there's always something left. And he had, due to these early reports and these implications of very high temperatures, he wanted to take a look at the dust himself. And the first sample he got was from Janet McKinley. He put it under the electron microscope. And this is the picture you see up here to your left. Most of the dust had irregular shapes of what you would expect from pulverized concrete. But some of the particles are perfectly round. And if you take a plastic bag of the dust and a very strong magnet, and you pull the magnet along the plastic bag, something comes along. And you all know if something comes along, a magnet, it's because it can become magnetic, because there's iron in it. Because what comes along is, to a very large extent, these perfectly round spheres. And here you see the spheres in close-up. It is iron. Now, how come? Well, maybe I should show you that an experiment that Stephen A. Jones did with the commercial diamond. You can buy thermite if you wish and play around with it in your backyard. I would not suggest it. Please remember to put on Google's protected. And but he did this in the corner of the lab, and you will see this sputtering, very violent reaction as we observed on the French part. And after the reaction was over, he collected the dust which inevitably fell around this reaction site, and it looked like the picture to the left. So this is what you get from reacting an ordinary thermite, and this is the picture I just showed you from the WTC dust. Now, how could we know how that this is exactly the same material making these spheres here and here? We are applying a technology called energy dispersive spectroscopy, which means that you direct the beam of electrons at a specific site on these particles. And we can do this with an accuracy better than 1/10,000th of a billion, 100 nanometers. We can point our electron beam at a specific spot. Now, the material responds by sending out X-rays. And this X-ray is coming out can be analyzed. And the spectrum looks like this. So each line is characteristic of a specific element. Fe means iron, Ca means calcium, K means potassium, Si for silicon, Al for aluminum, magnesium, sodium, iron, another iron line. And what you see from the World Trade Center dust, the same lines, you see iron here, calcium, potassium, silicon, aluminum, magnesium, and iron. There also is a little sulfur peak here in the dust from the this is a contamination from wallboard, which is calcium sulfate. There's sulfur in wallboard, bound to the sulfate. And many of the gentlemen here probably knows that wallboard is a wonderful material you can use for, you can put sparks in it. And the whole center of the towers were covered with wallboard, gypsum. It's a very efficient fireproofing material. So this is simply contamination from wallboard. Now, the important point here is what possibly can make an iron particle so perfectly round. The only explanation is that this particle has been modeled and it's been upflying. It's a property of droplets. They are, by nature, completely round due to an effect called surface tension. So if you have a close-up look of, say, ordinary frog in a microscope, all the small fat pearls in the skin, you'll observe that they're completely round. So this iron particle here has been offline. There's no doubt this is from the thermite reaction. Yes, please.
Are you saying it's not flying?
Yeah, it's flying in the air. Okay, this is, it has to be when it's not. Yeah.
Airborne.